In the last video, we just learned how to build a neural network. However, we still haven't had a chance to play around the skills and code with a dataset. So I've prepared a programming exercise for you to practice. Let's go through it together. This exercise is revised based on the TensorFlow tutorial. Please feel free to refer to their webpage as well if you want to know more. The links can be found in the bottoms of this notebook. What we are going to do in this exercise is to classify the image of clothing. We are going to train a neural network models to classify different types of image to identify what they are. Say, for example, sneaker, shirts, and so and so. We are going to use a TensorFlow carrots to build and train the model with the use of TensorFlow. First thing first, we are going to import the library. Few libraries that we are going to use, of course, we are going to use the TensorFlow, and also we are going to use some NumPy functions for us to separate the data sets nicely. Because we want to plot something, we are also going to use the matplotlib. And now, just take a look on these libraries first. And I also want to print you out the TensorFlow versions so that you know which versions that I'm using. Now, let's take a look on the data set. What we're going to play is a fashion MNIST. This is intended to serve as a direct drop-in replacement for the original MNIST dataset for benchmarking machine learning algorithm. Just in case, if you are not familiar with the original MNIST dataset, don't worry. This is just a dataset for handwritten digits 0, 1, 2, and so and so. But instead, for this fashion MNIST, this is a slightly challenged problems than the classic one, and it's focused on clothing. In this factions MNIST dataset, it contains 70,000 grayscale image in 10 categories. We will go through these labels later on and also their descriptions. But for the time being, just consider that these 10 categories has been identified in each of different types of the labels. Say, for example, 0 represent the t-shirt, and 1 represent the trousers, and so and so. And then each sample is a 20 by 28 grayscale image. That means we have one less channel because this is a grayscale, and the image pixel is 28 by 28. This is some examples of the dataset, how it looks like. Please also feel free to go through this reference if you want to know more about this dataset. The fashion MNIST data can be imported and loaded directly from TensorFlow because they are already prepared for use to play around. Just like what I mentioned, we have a 70,000 image, but the dataset already helps you to separate them into the training image and also the test image. Therefore, the dataset contains 60,000 20 by 28 by 28 grayscale image with the 10 fashions category, along with a test set with 10,000 image. So if we load the data, it will return you 4 NumPy array. That includes the train image that contains the 60,000 28 by 28 dataset. And then you will have their corresponding labels that is like a vector with 60,000. And of course, you will have the test image and also the test labels with the similar logics. Say, for example, 10,000 28 by 28 for the test image. And then you also got a 10,000 vector that represents the test image label. Now let's load the dataset. And then once we load the dataset, we load the dataset. We try to separate this dataset with the train image, train labels, test image, and test label with 4 NumPy array. And we also would like to provide the labels name, the corresponding class names in a list. So these lists is just like what I mentioned before in this table. You can see that the label 0 represent the t-shirts, label 1 represent the trousers, and so and so. And let's take a look on the data that we have. Explore a little bit of the data. Let's print out the shape. Just like what I mentioned before, the shape of the training image is 60,000 28 times 28. That is 60,000 samples. And then the shapes of the labels, this is like a vector, 60,000 as well. And then let's take a look on the shapes of the test image. Similarly, we have the 10,000 28 by 28 test image. And we also have their corresponding test dataset label, a 10,000 samples vector. And the label range, data range, that is from 0s to 9, that are represented by each of the class. Say, for example, 0 represented by t-shirts and top, and so and so. And then for the pixel value, let's take a look on the pixel value. That is between from 0 to 255. And here, this is the plot of the figures of the image that we have. Say, for example, the first image is an ankle boots, and then the second image is the t-shirt or tops, and so and so. Because these pixel value is ranged between 0 to 255, normally we need to do a normalizations. And data normalization is very common in machine learning to make the models training less sensitive to the scale of the features. This allows the models converge to better rates and in turn lead to a more accurate model. In practice, normalizations refers to rescaling the real value numerical attributes into a range between 0 to 1. And data will be normalized before feeding them to the neural network. It's important that the training set and also the testing set be processed in the same way. In this case, the pixel value of both training and test image are divided by 255, divided by the maximum value. Now let's take a look at what happens. Test image and train image and test image by 255, and then I assign the train image normals, test image normals to store them. And let's take a look on the pixel. Now the pixel value range from 0 to 1, and then I change it for the CMAP to a binary so that you can see we still have the image even though we just changed the pixel from 0 to 1. Now we are ready to build the model. First thing first, we need to set up configure a sequential model. Just like what I mentioned before, carrots have two functions for you to build a model. One is the sequential way, and the other one is the functional API way. Here we try to use the sequential model to build and set up the configurations. First thing first, we just create a model object that is equals to tf that carries sequential model. Now we are going to use the sequential models. That means we need to use the Dogfit functions to continue to add the layers to this model. The first model that we would like to have is a flattened layer. These flattened layers transform the format of the image from a 2 dimensions array that we have 20x by 20x pixel to a 1 dimensional array that is 20x times 20x. That means 784 pixel. So we try to flatten this image. And then the next two, and this layer has no parameters to learn. That means it only serves to reformat the data by unstacking the row of pixels in the image and lining them up. And then for the second and third layer, after the pixels are flattened, the network consists of a sequence of 2 dense layers. And these dense layers are densely connected or fully connected. They have their own activation functions. The first one is a value. We will talk about that later on. And then for the second one is the activation softmax activation functions. The second layer has 120x neurons. And then the last layer, that is the third layer, has 10 nodes, which returns a logic array with length of 10. And each of the nodes contains a scores that indicate the current image belongs to one of the 10 classes that we have. Now let's run the cell, and we just summarize this model. And you can see there are no parameters in the first layer because there's nothing to learn from this layer. We just try to flatten out the image from a 2 dimensions array to a 1 dimension array. And then there are 2 more dense layers that we just add in, and stacked together, they are fully connected together. And there are some parameters, of course, because they learn something from the image. They try to understand the image to learn the features from the image. And then finally, in the last layer, they use these learned features to return you a logic array with length of 10. That means it tries to predict what kind of image that the current image, that the current input belongs to. And then the second step is to compile the model. When we compile the model, there are 3 key arguments. There are 3 key parameters that we need to put in this compile model. The first thing is that we need to set up an optimizer. We need to decide what kind of optimizers that we are going to use. There are quite a number of optimizers, and we will talk about that later on as well. And in this case, we try to use one of the commonly used optimizer called Adam. And then we need to assign the loss functions. And finally, we need to assign the metrics. And here, the loss functions that we are using is a sparse, categorical, cost entropy. Because if you still remember this case, we have 10 classes. That means we need to use categorical cost entropy. Here, we have a from logic equals to false. Let's take a look at what it means. Sparse categorical cost entropy and categorical cost entropy both compute the categorical cost entropy. The only difference between that one have the sparse, without the sparse, or with the sparse is that it comes from one's hot representations. The one without the sparse is the categorical cost entropries can be used when we have a one-hot representations. That means we have something like this. Let me type it out for you. Let me insert above. For example, we have the first one. We have the first target that has 1 in the first sample. And then we have the second target, second label in the second sample. And then we have so and so. And then we have the third labels in the third sample, and so and so. And this is like a one-hot representations. In that case, we are going to use the categorical cost entropy. However, in our case, we are not using that. We are using the labels as an integer. That is 0, 1, 2, something like that. And then say, for example, if I want to change it to a just for labels as integer, that means the first one, we have the first sample. The first one is 0, the target is 0. And then the second one, we have 1 that represent the first our second target. And then in the first sample, we have the third label, and so and so. And then in this case, we need to use the sparse categorical cost entropy. Let me delete this cell first. Here we go. And then from logics equals to false. This is an argument informs the loss functions whether the output is expected to be a logic sensor. That's it, whether the tensor has been normalized or not. By default, from logic is false, which assumes that the output encodes a probability distribution, such as output from softmax or sigmoid activations function. Here you can see that the last layer we're using the softmax activation functions, and then in that case we just keep it as the default or put it as a from logic equals to false. However, if from logic is equals to true, this means the output is a logic. In this case, softmax or sigmoid activations will automatically apply that on the output value by the loss functions. And hence, output layer does not need any probabilistic activation functions. And then here, let's take a look on what we need to do. We just need to change it to the dense, we just continue to keep it as the dense layer. However, we will remove the activation function. And then we can set the from logic equals to true. And then in that case, there's no activation function is going to use in the output layer because if we use the from logic equals to true, this will automatically help us to do so. In this case, softmax and sigmoid activation functions will automatically apply that, and we do not need to input any activation function, assign any activation functions for this layer. And then now we are ready to train the model. To start the training, model Dogfit methods can be used to fit the model with the training data. The first one, that is your sample, that is your training data, and these contains the features. And then the second argument is the labels. That means that is your target with the associated training image. And then here we just assume we're going to iterate it by 10 times. That means we need to set it to a epoch equals to 10. Of course, you can change to whatever numbers that you want. However, if you increase these numbers, you need to be careful with the overfitting problems. And we will also cover in a later course. Let me run this out and see what happened. Okay, let me get one to run this out. Let me run the compile, and then let me fit the model. For 10 epoch, it doesn't take too long. I guess it takes less than 1 minute for us to train it up. And in the final epoch, you can take a look on the accuracy that is coming from the metrics that we set here. That is the accuracy. Because the loss functions, we do not quite able to interpret these loss value. In many cases, we will just set up a matrix for us to understand how well the model is performing. In this case, we try to use the accuracy to justify, to have a kind of understanding about the final model. And you can see that the training accuracy is up to 91% after 10 epoch. Now we can evaluate the model with the use of test image and also the test data. We can just use and evaluate functions by providing the test image and test label, and it will return us the two things that we built that we embedded in the model. The first is the loss function, and the other is the accuracy. And let's take a look. Now you can see that the test accuracy is around 86%. It turns out that the accuracy on the test dataset is a little less than the accuracy of the training dataset. And this gap between the training accuracy and test accuracy sometimes represent the overfitting. And overfitting happens when the machine learning models prefer, and that is our test image. An overfit model memorizes the noise and details in the training dataset to a point where it have a negative impact on the performance of the models in the new, previously unseen data. In other words, its generalization's ability is quite poor. And in this example, the test accuracy is not too bad, but there's a little bit overfitting. Now let's take a look to see how we can make predictions with the use of the model. To make predictions, image can be fed into the trained network. We just need to use the Dogpredict function, and then we can use the text image, and then we can put an image input, and then to make the prediction. A prediction is an array of 10 numbers. They represented the model's confidence to that image corresponding to each of the 10 different articles of the clothing. The highest confidence value indicates the predictions because remember that we are using the softmax functions. Here we go. We are using the softmax function, activation function. As a result, they represent the model's confidence for each of the corresponding image, and the highest confidence value indicates the predictions. And in this example, we just use the test image as an input for this predict function. And then to make some predictions, of course, in reality, you can use any other image with the 20x by 20x pixel to see whether or not that this image belongs to which class. But in our example, we just try to use back the text image to do such predictions, just for illustration purpose. Now let's take a look at the first prediction. These are the value from the first predictions. Just like what I mentioned before, a prediction is an array of 10 numbers. Here we have the 10 numbers, and each of the numbers represent the model's confidence to the corresponding image. And then in this case, the highest confidence value indicate the predictions. Let's take a look on the highest confidence belongs to which class. In our example, the highest confidence is number 9. That is our last value here. And that predicts the class and angle boots. The model is most confident that it's an ankle boot. Let's examine the test labels to see if it predicts it correctly. Now let's run this out. Excellent. The model predicts it correctly. Finally, we can verify and visualize the predictions. With the training network, just like what we mentioned, we can use the Dogpredict functions to make the predictions. And then let's predict a 16 image, and the correct image are shown in blue color, and the incorrect predictions labels are in red. The numbers indicate the percentage, that means that is the confidence for the predicted label. Let me run this out and see what happens. Excellent. The model predicts all 16 images correctly. Just a very friendly reminder, the models can be wrong even when it has a high confidence about its prediction. We just try to verify and visualize the predictions from the testing image, and also we try to make predictions based on the testing image. In reality, sometimes we wanted to use the trained models from the image that do not belong to these training and testing data sets. Let's take a look to see how we can use these trained models to fit an image for the prediction. Let me try to grab an image from the original test dataset. We have a 20x by 20x pixel. We remember that the TensorFlow Keras models are optimized based on batch or collections of examples at once. Therefore, even this is a single image predictions, image needs to be added into a list to make it like a batch. In that case, we're going to use the expand dimension functions to help us to insert a new axis that will appear at the axis positions in the expanded array shape. And in this case, we just want to use these expanded dimension functions to expand it just like expand the image to make it just like a batch. And then the image can be fed into the model for prediction. Again, we use Dogpredict functions to make the predictions, and then we use a NumPy functions .argumentMax to find out the maximum confidence positions. That means to find out the predicted class. Let's take a look. And then the highest confidence belongs to 4, and then the predicted class is a code. Let's visualize the results to see if the models predicted correctly. Excellent. Again, the model predicts the labels correctly. That's it for these videos and course. The purpose of this exercise is to let you have a better understanding about the entire process on building a neural network model. From capturing the data, to exploring the data, to normalizing the data, to configuring the neural network, to compiling and fitting the models, and finally, to evaluating the model. Some of the key techniques and terms we mentioned might be too brief here, such as the value activation functions, Adams optimizer. In the next course, I will cover the advanced techniques in details so that you can build your models systematically and comfortably. See you in the next course.